All right, good morning, good afternoon, good evening, ladies and gentlemen. Welcome to this series of online lessons. If you haven't already, subscribe to the channel, leave a like for this video, and comment. All right, now in today's lesson, we are with a tutorial sheet from the University of Zambia, and I specifically chose this tutorial sheet because it also connects to what I think I have made most videos on, and that is on vectors. So this is on equilibrium, static equilibrium. So equilibrium simply means everything is balanced out. There is no net force. So if you have a box like that, meaning that the force pulling this side and the force pulling that side are the same. Okay, force 1 and force 2 are the same. Otherwise, if this force pulling here is greater, then the box will most likely move this direction. And if this force right here behind is greater, then the box will move that way. So in equilibrium, we're just talking about balancing forces. And if all the forces are the same, then meaning that when you sum all the forces acting on the object, they should give you 0 because they are the same. And like the example that we gave here, so if the force acting forwards here, forward, and the force acting backwards here are the same. So since this is in the negative direction and this is in the positive direction, when you add F1 plus this one is negative F2, this will give you 0. So that is the basis of a static equilibrium. So we're just looking at vectors, forces, and so on and so forth, and we are adding them to 0, right? Or we are equating them to 0. And basically, having that known, if we sum forces in the x component or vectors in the x component, just like we were resolving those vectors, so vectors in the x component also add up to 0, and vectors in the y component also add up to 0. So if you understood resolving vectors into components, this would be a walkthrough. Okay, so but basically this is what we'll be doing for us, or this is what we'll be using for us to find the tensions and the missing masses in all questions on static equilibrium. So we're just making use of the concepts that we learned in vectors. And in addition to that, we're just considering that the forces in the x component all add up to 0, and the forces in the y component all add up to 0. And the other thing that you just need to know here is how to solve systems of equations or simultaneous equations. All right, so we can start. So now, what you should know is that tension comes from the force acting on mass. Okay, so for instance, this tension here goes all the way through to that mass here. So that is to say the force acting here is the same as the force in the string, because again these are they're in equilibrium. So the force down here is the same as the force in the string there, and the force in this string from here going down is the same as the force on this object. So and the force in this string all the way to the wall there is the same as the force pulling away from the string, which is based on Newton's third law. Okay, so yeah, so basically that is what we need to know. Since these are in equilibrium, this tension that is here is the same tension going through there, because here there will be a tension up and a tension down. So the tension up is this tension here, and the tension down is this force. And if these are equal, then it's equal throughout. Same applies here. The tension there will be the same as the tension down there, because these are in equilibrium. Yeah, so basically that's it. So now let me just draw it properly so that you can see this well enough. So there is this tension. Okay, so there is this tension, then there is this tension, and there is this tension. Okay, and we have resolved that this tension here is the same as the tension in the here. So we can now read through the question, and we can answer this question. So the system in the figure is at equilibrium when M1 is 10 kg. So M1 is 10 kg. So if this is 10 kg, we can find the weight, which is just the force that will act downwards here. So the weight, which is force, we know that force is mass times gravity, and gravity is 9.81 more precise. So this would be the mass, which is 10, times the gravity, which is 9.81. So this mass, or this weight on this mass, is 98 newtons. Okay, so the system, which is this system, is at equilibrium when the mass is 10 kg or when the weight is 98 newtons. Find the value of tension 1, tension 2, and M2. Okay, so tension 1 we've already found. So since this is the same tension throughout there, so this will be 98 newtons, which is the same answer here. So here tension 1 equals to 98 newtons. Okay, so that was easy. Now we can use tension 1 to find the other tensions, and what we'll do is, first of all, we'll create an x or y plane and use green plane. Okay, so we'll create an x or y plane. That. Then what I'm going to do is lift just this up and bring it from the x or y plane like that. Okay, let me push this downward. All right, I have managed to pull it up. So basically we have tension 1 here. So we have tension 1 there, which is 98 newtons, and it is suspended at 45 degrees from the horizontal. Then we have tension 2 there, which is suspended 53 degrees from the negative horizontal. And we have our M2. Okay, so now remember what we said, vectors in the x component add up to 0 and vectors in the y component add up to 0. So remember what we said, x component involves the cos function, and y component involves the sine function. So what we're just going to say is that vectors in the x add up to 0, and when we sum vectors in the y, they should all add up to 0 as well. So for this question, we'll just find the vectors in the x. I'll put in red. So this vector in the x is 98 cos the angle at which it is suspended from the positive horizontal, which is 45 degrees. We go to this tension, which is tension 2, so plus tension 2 cos the angle which it is displaced at is the angle from the positive horizontal going there. Okay, since this is a straight line and we have 53 there, so we subtract 53 from 180, which will give us this angle as 127. So this is 127, and so this angle here is 127. Then finally we have this one. So from here going all the way there, that is 270. So that is plus m2 cos 270. And we said forces in the x, so these are equal to 0. Okay, we do the same for forces in the y. So forces in the y will just replicate the same thing. We just change the sign there. So this would be 98 sine 45 plus t2 sine 127. Let me use a different color for the forces in the y. So let me use this. So that would be 98 cos 45 plus t2 cos, it's supposed to use sine, sorry. So that is for the y. For the y, we have 98 sine 45 plus t2 sine 127 plus m2 sine 270 is equal to 0. So what we've done here is we've found the sum of the x component and we've equated to 0, and the sum of the y component we've equated to 0 as well. So let me just move this on blank canvas so that I can work it out properly. Okay. Okay, start from there. All right, so we have our x component and our y component vectors, so we can simplify these. So 98 cos 45, so that is 98 times cos 45, which is giving me 69.2964646. So don't round off yet, plus t2 cos 127, so cos 127, that will give me negative, so this will be negative 0.6018150. Okay, I can end there. 2 3, let's put 2 3 there. Then t2, then plus m2 here, cos 270 is 0, so cos 270 is 0, so we can just leave it like that and not write anything. So cos 270 is 0, so there is nothing there, but we have an equal to 0 here. Then for this one we can also simplify, so we can also simplify that. So that is 98 sine 45. So that's 98 sine 45, which is giving me 69.2 as well. 9.2964646. Then t2 sine 127. So sine 127 is giving me positive 0.79863551 t2. Okay, then plus m2 sine 270, that will give me negative, so this would be negative m2 would be equal to 0. Okay, so now here we can just remain with values on one side, and we take variables on the other side as well. We just rearrange everything. So this can be written as negative 0. Let me use color. So this would be negative 0.6018150023. T2 is equal to negative 69.2964646, and we have this other one. So here I can find T2 by dividing actually both sides by negative 0.6018150023, and this side the same thing, negative 0.6018150023. Then when I divide that, this is giving me a tension T2 of about 115.14. Okay, then I can use this to find my M2 here. So what I'll basically do is this would be 69.29646456 plus 0.79863551 times T2, which is 1, right, which is 115.14. We can transpose this side. This becomes equal to M2 right there. So we can simplify this to get our M2. So this is 69.29646456 plus 0.7986 open brackets 115.14. When I sum this, it is giving me M2 as 161.25 newtons. So this is in newton, and that is how you find your tensions. Okay, so let's see. So, yeah, so that is about it. So these are the answers here. So this converted to newtons. Oh, actually this is a mass. M2 is a mass, so we can convert this to kgs by dividing by approximately 10, or say 1.6, 1.25 divided by 9.8. This will give us about 16.45 kgs, and we are done. So basically that is how you work out these problems. So the key ideas is the forces in the x add up to 0 and the forces in the y add up to 0, and the sum of the forces in the x and in the y add up to 0. So you just resolve those in components and you're done. Have a great evening.